You checked the weather this morning, maybe glanced at your phone, saw some rain coming, seemed normal. But right now, while you're listening to this, multiple severe storm systems are simultaneously tearing across the Gulf Coast. Arctic air is plunging temperatures to dangerous lows 1,500 miles north. California is drowning under a relentless winter deluge, and the sun just unleashed another barrage of X-class flares toward Earth. All of this, at the same time, within 48 hours. This isn't coincidence. This is synchronized atmospheric chaos on a scale meteorologists rarely see outside of late spring, and it's happening in mid-February. Something has shifted in the engine that drives our weather, and if you stay with me until the end, you'll understand why the worst might still be coming. Subscribe to follow this story to its conclusion, because what happens tonight across the Gulf Coast is only one chapter. The jet stream remains amplified, the pattern still locked in place, and the conveyor belt of instability continues running toward an endpoint we can't yet predict. Communities brace, forecasters recalculate, and somewhere over the warm Gulf waters, the next round of storms is already organizing. You'll want to know when it finally breaks. You probably checked the weather app on your phone this morning and saw some rain in the forecast. Maybe you noticed a thunderstorm warning scrolling across the bottom of a news channel. It seemed ordinary, just another February day. But what's racing across Texas right now, barreling toward Louisiana and Mississippi by tonight, and preparing to slam into Alabama, Georgia, and Central Florida by tomorrow, isn't just another storm system. It's something stranger, something synchronized. And the deeper you look, the less it resembles the weather patterns we've come to expect. Right now, multiple severe thunderstorm cells are organizing into a continuous corridor of violent convection stretching from the western Gulf Coast all the way to the Atlantic. Meteorologists are watching this unfold in real time, and what makes their screens glow with concern isn't just the intensity of individual storms. It's the structure. This outbreak is exhibiting a dual-mode behavior that makes it uniquely dangerous. Some cells are organizing into discrete supercells, the kind that spin like tops and drop tornadoes onto the ground. Others are forming linear squall lines, vast walls of wind and rain capable of producing widespread damage across hundreds of miles. Having both modes active simultaneously in the same outbreak is like watching two different weather events merge into one continuous threat. The timing alone should make you pause. We're in mid-February. Tornado season in the United States typically peaks between April and May, when the jet stream positions itself just right and Gulf moisture collides with dry continental air in that perfect recipe for atmospheric violence. But here we are, weeks before spring officially begins, and the atmosphere is already firing on all cylinders. This isn't supposed to happen yet. The calendar says winter. The storms say otherwise. What's powering this early surge? Start with the Gulf of Mexico. Water temperatures remain unusually warm for this time of year, pumping moisture into the lower atmosphere like a massive evaporative engine. That warm, humid air is now streaming northward, carried by southerly winds ahead of a powerful cold front advancing from the west. When these two air masses collide, the atmosphere doesn't negotiate. It explodes upward. Instability gradients form along the boundary, and where you have instability, you have fuel for thunderstorms. But not just any thunderstorms. The kind that meteorologists describe with words like explosive convective development. The kind that turn the sky green and make sirens wail. Now, you might think early season severe weather is just an anomaly, a weird blip on the radar, and you'd be partially right. February outbreaks are rare, but they're not unprecedented. Go back to February 2nd, 2008, and you'll find what meteorologists still call the Super Tuesday outbreak. That system tore through the South on a winter evening, spawning dozens of tornadoes and killing 57 people. It was a reminder that the atmosphere doesn't always respect our seasonal calendars. And that's the unsettling part. If the climate system is capable of producing these anomalies, What's stopping it from producing them more often? Some researchers are now exploring a concept they call seasonal phase acceleration. The idea is simple, but troubling. The atmosphere, influenced by a combination of jet stream dynamics and persistent moisture availability, begins behaving like it's already weeks ahead in the calendar. February starts to look like March. March starts to look like April. The severe weather season doesn't necessarily intensify, but it stretches. It starts earlier and potentially extends later. If that's happening, and the evidence is still emerging, then what we're watching tonight might not be an isolated event. It could be the opening act of a longer, more volatile spring storm cycle. Think about what that means. If severe season is starting early, emergency managers and forecasters have less time to prepare communities. Public awareness campaigns designed for March and April are still weeks away. People aren't mentally conditioned yet for tornado warnings. Schools haven't conducted spring drills. The psychological and logistical infrastructure we rely on to minimize casualties during severe weather season hasn't fully activated. But the storms don't wait for us to be ready. And here's the bigger question, the one that keeps atmospheric scientists awake at night. If this is just the first pulse, what comes next? Severe weather outbreaks don't usually occur in isolation. They're often part of a larger pattern, an atmospheric configuration that persists for days or even weeks. If the jet stream remains locked in its current amplified state, if the Gulf continues feeding warm moisture northward, if the cold air reservoir over Canada continues spilling southward at regular intervals, then we might not be looking at one outbreak. We might be looking at the beginning of a prolonged, severe weather regime. Multiple rounds, multiple threats, a conveyor belt of instability marching across the same regions again and again. So when meteorologists say the worst is still coming, they're not just talking about tomorrow's storms. They're talking about the possibility that this entire season could unfold differently than anything we've prepared for. And what makes it even more disorienting is that this outbreak isn't happening in a vacuum. While the Deep South braces for tornadoes, something equally extreme is happening everywhere else. While storms race across the Gulf Coast, another phenomenon is simultaneously unfolding 1,500 miles to the north. Arctic air, the kind that belongs in January, is plunging southward into the eastern United States with a ferocity that makes February feel like the dead of winter. Temperatures are dropping into the teens and single digits across the Midwest and Northeast. Wind chills are falling below zero. People are scraping ice off windshields and bundling up in layers they thought they'd already retired for the season. This isn't a subtle cold snap. This is a full-scale Arctic invasion. And it's not even the coldest air available. Meteorologists tracking the upper-level flow can see even colder air still pooled over northern Canada, waiting like a reserve force. The cold front driving tonight's severe weather outbreak is the leading edge of this Arctic mass, and the contrast between the frigid continental air and the warm Gulf moisture is precisely what's generating the explosive instability. But that same Arctic air, once the storms pass, will flood southward and eastward, replacing the warmth with bitter cold. It's a meteorological 1-2 punch. First the violence, then the freeze. Meanwhile, off the coast of the Carolinas, residual energy from a recent bomb cyclone continues to spin. The storm itself has weakened, but it's left behind a sprawling circulation, generating persistent coastal winds and unusual snow cover across parts of Georgia and South Carolina. Snow in Georgia, in February. It's not unheard of, but it's uncommon enough to disrupt daily life. Roads close. Flights cancel. The landscape transforms into something unfamiliar. Now shift your attention 2,500 miles west to California. While the South battles tornadoes and the East shivers under Arctic air, the West Coast is absorbing a massive winter storm that forecasters are describing as a significant precipitation event. Snow is piling up in the Sierra Nevada, delivering long-awaited relief to a region that has spent years oscillating between drought and deluge. The snowpack, crucial for California's water supply, is finally building. But that same storm system is also triggering flood warnings in lower elevations and raising concerns about mudslides in areas scarred by recent wildfires. Burn scars don't absorb water well. When heavy rain falls on exposed soil, the runoff accelerates, carving channels and destabilizing hillsides. Communities downstream are watching the skies nervously. And if you think that's the extent of the chaos, look across the Atlantic. Europe is dealing with its own hydrological nightmare. Storm Marta, which battered northern Europe with gale-force winds earlier this week, has weakened, but the damage lingers. Soils across the United Kingdom, France, and Germany remain saturated from weeks of above-average rainfall. Rivers are swollen. Flood defenses are strained. The ground simply can't absorb any more water, which means even moderate rainfall now translates into immediate runoff and rising water levels. Entire communities are sandbagging their homes and businesses, preparing for rivers to overtop their banks. So let's take a step back and look at what's happening simultaneously across the Northern Hemisphere. You have severe thunderstorms and tornadoes in the southern United States. You have Arctic air plunging into the east. You have bomb cyclone remnants spinning off the Atlantic coast. You have a major winter storm dumping snow and rain across California. You have persistent flooding across northern Europe. All of this at the same time, within a 48-hour window. This isn't normal variability. This is synchronized chaos. Meteorologists have a term for what's driving all of this. It's called an amplified jet stream pattern. The jet stream, that high-altitude river of air that circles the planet, isn't flowing smoothly west to east like it typically does. Instead, it's buckled into exaggerated waves, forming massive ridges and troughs that stretch from the Arctic to the subtropics. These waves are called Rossby waves, named after the Swedish meteorologist Carl Gustaf Rossby, who first described them in the 1930s. Under normal conditions, Rossby waves are relatively gentle, producing the kind of weather variability we expect week to week. But when they amplify, when the ridges rise higher and the troughs dig deeper, the weather extremes intensify. Think of the jet stream as a boundary between cold polar air and warm tropical air. When that boundary meanders wildly, it brings Arctic air much farther south than usual and pumps tropical moisture much farther north. The collision zones where these air masses meet become battlegrounds for severe weather. The ridges where warm air surges poleward can produce heat waves and drought. The troughs where cold air plunges equatorward can produce blizzards and ice storms. And right now, the jet stream looks like a roller coaster track, with peaks and valleys so pronounced that weather extremes are erupting simultaneously across multiple continents. What makes this pattern particularly concerning is the synchronization. Amplified jet streams have occurred before. Multi-hazard weather events have occurred before. But having this many extremes clustered together in such a short time frame suggests the atmosphere is in a highly energetic and unstable state. It's as if the entire system has shifted into a higher gear, churning out weather events faster and more intensely than the seasonal average would predict. And here's where it gets speculative, but grounded in emerging research. Some atmospheric scientists believe that when the jet stream locks into these amplified patterns, it can persist for extended periods, days, or even weeks. If that's what's happening now, then tonight's severe weather outbreak might be just the first installment. The pattern could produce multiple rounds of storms, each one tapping into the same atmospheric ingredients. The Arctic air could continue surging southward in waves. The California storms could keep rolling in from the Pacific. Europe's flooding could worsen. We might be at the beginning of a prolonged period of atmospheric turbulence, not the middle or the end. But why is this happening now? Why is the jet stream behaving so erratically in mid-February 2025? That question leads us into murkier territory, where established science meets emerging hypotheses, and where the answers are less certain, but far more intriguing. There's a question meteorologists have started asking more frequently in recent years, usually in hushed conversations at conferences or buried in the discussion sections of research papers. It's a question that sounds simple, but carries enormous implications. Is tornado season moving? For as long as we've kept records, the United States has experienced a predictable seasonal rhythm of severe thunderstorms and tornadoes. Spring, particularly April and May, is prime time. That's when the jet stream dips far enough south to create the necessary shear, when Gulf moisture becomes abundant, when daytime heating destabilizes the atmosphere, the ingredients align, and the storms fire. Summer brings different challenges, mainly excessive heat and isolated severe storms. Fall and winter are typically quieter, with occasional outbreaks, but nothing like the sustained fury of spring. That rhythm has governed emergency preparedness, public awareness campaigns, insurance models, and even agricultural planning. We've built entire systems around the assumption that severe weather follows a calendar. But what if that calendar is shifting? The Deep South, stretching from eastern Texas through Louisiana, Mississippi, Alabama, and into Georgia, has always been vulnerable to tornadoes. The region sits at the intersection of multiple air mass source regions: cold air from Canada, dry air from the desert Southwest, warm, humid air from the Gulf of Mexico. When these air masses collide, the atmosphere doesn't hesitate, it convulses. But historically, the worst outbreaks occurred later in spring, not in February. What we're seeing tonight, a significant severe weather outbreak weeks before the traditional peak, suggests something might be changing. One hypothesis centers on the Gulf of Mexico. Sea surface temperatures have been running above average for much of the past year, and that warmth doesn't disappear overnight. Water has thermal inertia. It holds heat. Even as winter settles over the continent, the Gulf remains relatively warm, continuing to pump moisture into the atmosphere. Higher sea surface temperatures mean higher evaporation rates. Higher evaporation rates mean more atmospheric moisture. More moisture means more fuel for thunderstorms. It's a chain reaction, and the Gulf is the ignition point. Now, add to that the behavior of the jet stream. Normally, during winter, the jet stream sits far enough north that severe weather ingredients struggle to come together over the deep south. The shear is there, the cold air is there, but the moisture and instability are limited. But if the jet stream dips southward earlier in the year, or if warm Gulf waters allow moisture to penetrate farther north even during winter months, then you start to get environments capable of producing severe weather outside the traditional season. The atmosphere doesn't care what month it is. It only cares about the ingredients. And right now, the ingredients are aligning in February. Some climatologists have started documenting statistical trends, suggesting that certain severe weather events in the southeast are indeed occurring earlier in the calendar year than they did decades ago. The data isn't overwhelming yet, and attribution is tricky, but the signal is there. Fewer big outbreaks in late May and June. More activity in February and March. It's subtle, but it's measurable. They call it seasonal compression. The idea isn't that we're necessarily getting more tornadoes overall. The total number might stay roughly the same. But the distribution is changing. The season is starting earlier and potentially ending earlier, compressing the window of peak activity. If that's true, it has cascading implications. Forecasting models are trained on historical data. They learn patterns based on decades of observations. If the patterns are shifting, even slightly, the models might struggle to capture the new dynamics. A model calibrated to expect peak tornado activity in April might underestimate the risk in February. An underestimation leads to underpreparedness, which leads to higher casualties when storms do strike. There's also a psychological dimension. People living in tornado-prone regions develop an internal calendar. They know that by March or April, they need to start paying closer attention to the sky. They check their emergency kits, they review their safe spots, but in February, most people are still in winter mode. They're thinking about heating bills and snow days, not tornadoes. When a severe weather outbreak strikes outside the expected window, it catches communities off guard. The warning system still functions, the sirens still sound, but the mental readiness isn't there. And in a tornado situation, seconds matter. Now, here's where the science gets contentious. Some researchers have proposed that the shift toward earlier severe weather outbreaks might be connected to broader climate trends. Specifically, the idea that a warming climate is altering the seasonal availability of moisture and instability. The hypothesis goes like this. As global temperatures rise, even modestly, the atmosphere can hold more water vapor. Warmer Gulf waters evaporate more moisture. That moisture becomes available earlier in the year. Meanwhile, Arctic amplification, the phenomenon where the Arctic warms faster than the rest of the planet, might be altering jet stream behavior, allowing it to dip southward at unusual times. The combination of earlier moisture availability and erratic jet stream dynamics could, in theory, shift the timing of severe weather season. But, and this is critical, the science is not settled. Long-term attribution of specific weather trends to climate change remains one of the most debated topics in atmospheric science. Correlation doesn't equal causation. Natural variability in the climate system can produce multi-year or even multi-decade trends that have nothing to do with long-term climate change. Teasing apart the signal from the noise requires decades of data, sophisticated statistical analysis, and a healthy dose of humility about what we can and cannot conclude. So when someone asks, is climate change making tornado season start earlier? The honest answer is, we don't know yet, but we're watching closely. What we do know is that the concept of fixed severe weather seasons might be becoming less reliable. The boundaries are blurring. The calendar is less predictive than it used to be. And that uncertainty, that erosion of predictability, is in some ways more unsettling than the storms themselves. We rely on patterns. We build our lives around expectations. When those expectations start to shift, even subtly, it forces us to recalibrate everything. But here's the part that really keeps you up at night. While all of this atmospheric chaos unfolds, something else is happening above the atmosphere. Something that, on the surface, seems completely unrelated, and yet the timing is impossible to ignore. On February 13th, 2025, the Sun produced an X-class solar flare. For those unfamiliar with solar classification, flares are categorized by their X-ray intensity. C-class flares are weak. M-class flares are moderate. X-class flares are the big ones, the kind that can disrupt satellite communications and, in extreme cases, damage power grids. The flare originated from an active region designated AR 4366, a sunspot cluster large enough to see with the naked eye through proper solar filters. It wasn't alone. Over the past week, the Sun has fired off multiple M-class flares and at least one coronal mass ejection, a massive eruption of plasma that hurtled through space and slammed into Earth's magnetic field. The effects were visible. Auroras, normally confined to high latitudes near the Arctic Circle, danced across skies as far south as the northern United States. People in Minnesota and Montana posted photos online of green and purple curtains of light shimmering above the horizon. Geomagnetic storms, rated on a scale from G1 to G5, reached moderate levels. Satellites experienced minor disturbances. Radio operators reported brief signal interruptions. It was spectacular, and for most people, it was harmless. Just a beautiful reminder that space weather exists. But here's the coincidence that captures the imagination. While the Sun unleashed this barrage of energy, Earth's atmosphere erupted into a multi-hazard weather pattern, unlike anything we've seen in months. Severe thunderstorms, Arctic air outbreaks, bomb cyclones, flooding in Europe, all of it happening within days of heightened solar activity. And human brains are wired to find patterns. We see two things happening at the same time, and we instinctively ask, are they connected? The short answer, according to mainstream atmospheric science, is no. Solar flares and coronal mass ejections do not cause thunderstorms, tornadoes, or cyclones. The energy mechanisms are completely different. Solar flares release X-rays and ultraviolet radiation that interact with the upper atmosphere, primarily the ionosphere. Coronal mass ejections deliver charged particles that disturb Earth's magnetic field. But thunderstorms form in the troposphere, the lowest 10 kilometers of the atmosphere, driven by temperature gradients, moisture content, and wind shear. The physics simply doesn't support a direct causal link. Solar energy doesn't penetrate deep enough into the atmosphere to directly influence convective processes. And yet, the question persists. Not because mainstream science is wrong, but because there are minority hypotheses, speculative but not entirely dismissed, that explore potential indirect connections. Let's walk through them carefully, with the understanding that these ideas exist at the fringes of research and are not widely accepted. First, there's the ultraviolet variability hypothesis. Solar flares temporarily increase the sun's ultraviolet output. That ultraviolet radiation is absorbed in the stratosphere, the atmospheric layer above the troposphere, where it influences ozone concentrations and temperature gradients. Some researchers have proposed that changes in stratospheric temperature could, under specific conditions, alter atmospheric wave patterns that eventually propagate downward and influence the jet stream. It's a long chain of causation with many weak links, and most atmospheric scientists remain skeptical. But it's not entirely impossible. Second, there's the energetic particle precipitation hypothesis. During geomagnetic storms, charged particles from the sun penetrate Earth's atmosphere near the poles, where the magnetic field funnels them downward. These particles can interact with atmospheric chemistry, particularly ozone. Changes in ozone concentrations can alter radiative heating rates. Altered heating rates can influence atmospheric circulation patterns. Again, this is speculative. The effects, if they exist, are likely small and difficult to isolate from the noise of natural atmospheric variability. Third, there's the cosmic ray modulation hypothesis, which is even more controversial. Solar activity influences the flux of cosmic rays, high-energy particles originating from outside our solar system. When the sun is active, its magnetic field deflects more cosmic rays, reducing their intensity at Earth. Some researchers have speculated that cosmic rays might influence cloud formation by providing nucleation sites for water vapor to condense around. Fewer cosmic rays, fewer clouds. More cosmic rays, more clouds. Changes in cloud cover could influence temperature and precipitation patterns, but the evidence for this mechanism is weak, and many experiments have failed to replicate the effect under controlled conditions. So why do these hypotheses persist? Partly because the universe is interconnected in ways we're still discovering. Partly because scientists are curious and willing to explore unconventional ideas. And partly because the human mind craves explanations. When we see extreme weather and solar activity happening simultaneously, we want a story that ties them together. It feels unsatisfying to say, it's just a coincidence. But coincidences do happen. In fact, they happen all the time. The sun goes through an 11-year activity cycle, oscillating between solar minimum, when sunspots are rare, and solar maximum, when they're abundant. Right now, in 2025, we're approaching solar maximum. That means elevated solar activity is expected. It's not unusual. Meanwhile, Earth's atmosphere is a chaotic system capable of producing extreme weather events at any time, driven by countless variables that have nothing to do with the sun. Two independently chaotic systems will occasionally synchronize purely by chance. That doesn't mean one caused the other. And yet, there's something psychologically compelling about the idea of a cosmic connection. It appeals to our sense of scale, our desire to see Earth as part of a larger system, influenced by forces beyond our atmosphere. The sun is our star, the source of all energy that drives weather in the first place. Solar radiation heats the Earth's surface unevenly, creating temperature gradients that drive wind, evaporation, and precipitation. Without the sun, there would be no weather. So it's not unreasonable to wonder whether variations in solar output might subtly influence the patterns we see. But subtle influence is not the same as direct causation. The energy from a solar flare, while impressive, is dwarfed by the energy already present in Earth's weather systems. So, where does that leave us? The mainstream scientific consensus is clear. Solar flares do not cause tornadoes. They do not trigger bomb cyclones. The correlation we're observing right now is almost certainly coincidental. But the minority hypotheses remind us that atmospheric science is still evolving, still refining its understanding of complex interactions. And sometimes the most interesting questions are the ones without definitive answers yet. But if the sun isn't driving the storms, then what is? The answer lies not in space, but in the dynamics of the atmosphere itself, and in a phenomenon that has become one of the most studied and debated topics in modern meteorology. If you want to understand why severe thunderstorms are tearing across the Gulf Coast, while Arctic air crushes the East and Europe floods, and California gets buried in snow, all at the same time, you need to understand one concept. The polar vortex. The term has been thrown around in media reports for years, often misused, often sensationalized. People hear polar vortex and imagine some kind of apocalyptic weather monster descending from the Arctic. But the polar vortex isn't an event. It's a permanent feature of Earth's atmosphere. It's a large-scale cyclonic circulation, a massive pool of cold air that spins counterclockwise over the North Pole throughout the winter months. Under normal conditions, the polar vortex remains locked in place, contained by a strong jet stream that acts like a fence, keeping the cold air bottled up in the high latitudes. But sometimes the polar vortex weakens. Sometimes it splits. Sometimes it gets displaced southward. When that happens, lobes of Arctic air spill out of the polar region and surge into the mid-latitudes, bringing bone-chilling cold to places that don't normally experience it. And when that Arctic air collides with warmer air masses, the temperature contrast intensifies, the pressure gradients steepen, and the jet stream responds by amplifying into those exaggerated waves we talked about earlier. This is what's happening right now. The polar vortex has been disrupted. Not catastrophically, not in a way that's breaking records, but enough to send pulses of Arctic air southward into North America and Eurasia. Those pulses are creating the temperature contrasts necessary for explosive storm development. The Arctic air diving into the eastern United States is colliding with warm, moist air streaming northward from the Gulf of Mexico. That collision zone is where tonight's severe weather outbreak is occurring. It's the battleground. Meanwhile, the same disrupted polar vortex is influencing weather patterns across the Atlantic. The jet stream over Europe has buckled into a pattern that keeps funneling storm systems across the United Kingdom and Northern Europe, one after another. Each storm dumps more rain onto already saturated soils. Rivers rise, flood defenses fail, and because the pattern persists, there's no relief. The atmosphere is locked in a configuration that favors continuous wet weather. Now, here's where it gets interesting. Polar vortex disruptions don't just cause a single weather event. They can trigger a cascade. Think of it like dominoes. The initial disruption sends a wave of energy propagating through the atmosphere. That wave amplifies the jet stream. The amplified jet stream steers storms into specific regions. Those storms create their own feedback loops, altering pressure patterns and temperature gradients, which further influences the jet stream. The system becomes self-reinforcing, at least for a period of time. Meteorologists call this a high-amplitude wave regime. The jet stream looks less like a gently meandering river and more like a series of sharp peaks and valleys. In the ridges, where the jet stream bulges northward, you get warm air advection, clear skies, and often drought conditions. In the troughs, where the jet stream dives southward, you get cold air advection, storminess, and precipitation. Right now, we're in a textbook high-amplitude regime. The trough over the eastern United States is deep, pulling Arctic air far to the south. The ridge over the western United States is pronounced, allowing California storms to track inland with unusual persistence. But here's the critical question: how long will this pattern last? Weather patterns typically evolve on timescales of days to weeks. A ridge builds, then breaks down. A trough digs, then lifts. The atmosphere doesn't usually stay locked in one configuration indefinitely, but sometimes, under specific conditions, a pattern can become quasi-stationary. The jet stream gets stuck. The same regions experience the same type of weather, day after day, week after week. And if that happens with a high amplitude pattern, the results can be devastating. Floods where the trough parks, droughts where the ridge persists, and for regions caught in the collision zones, repeated severe weather outbreaks. There's emerging evidence, still debated, that polar vortex disruptions might be occurring more frequently in recent decades. Some researchers attribute this to Arctic amplification, the phenomenon where the Arctic warms faster than the rest of the planet. The hypothesis goes like this: a warmer Arctic reduces the temperature gradient between the pole and the mid-latitudes. That temperature gradient is what drives the jet stream. A weaker gradient means a weaker, more meandering jet stream. A more meandering jet stream is more prone to amplification and disruption. Therefore, a warming Arctic could lead to more frequent polar vortex disruptions, and, by extension, more extreme weather events in the mid-latitudes. It's an elegant hypothesis, but it's not universally accepted. Other researchers point out that Arctic warming is occurring primarily during summer and fall, not winter, when the polar vortex is most active. They argue that natural atmospheric variability can explain most of the observed changes in jet stream behavior. The debate is ongoing, and the science is complex. What's clear is that the polar vortex is a critical piece of the weather puzzle, and understanding its behavior is essential for predicting what comes next. So, applying this framework to our current situation, what we're likely witnessing is a polar vortex-driven amplification event. The disruption sent Arctic air southward. The southward surge created temperature contrasts. The contrasts amplified the jet stream. The amplified jet stream is steering multiple weather systems into collision zones. The Gulf Coast outbreak, the California storm, the European flooding, they're all downstream consequences of the same upstream cause. And if the pattern persists, if the jet stream remains locked in this amplified configuration, then tonight's severe weather outbreak might be just the beginning. We could see multiple rounds of storms over the coming weeks, each one tapping into the same ingredients: the same Arctic air reservoir, the same Gulf moisture source, the same amplified jet stream steering mechanism. It's a conveyor belt of instability, and once it starts running, it doesn't stop easily. But even as we grapple with the immediate threats, even as communities brace for tonight's storms and tomorrow's cold and next week's floods, there's a larger question looming. A question about the future, about how our understanding of weather is evolving, and about what new tools we might develop to navigate an increasingly volatile atmosphere. Science doesn't stand still. While storms churn and patterns shift, researchers are constantly refining models, collecting data, and testing hypotheses about how the atmosphere works. And over the past decade, one area of research has exploded into prominence, driven by a simple observation. The jet stream seems to be behaving differently than it used to. The jet stream is born from temperature contrasts. Cold air is dense and sits lower in the atmosphere. Warm air is less dense and rises higher. Where these two air masses meet, particularly in the mid-latitudes, a temperature gradient forms. That gradient creates a pressure gradient. Air flows from high pressure to low pressure. And because Earth is rotating, the Coriolis effect deflects that flow, creating the westerly jet stream we observe at high altitudes. The stronger the temperature gradient, the stronger the jet stream. The weaker the gradient, the more the jet stream meanders. Now, enter Arctic amplification. Over the past several decades, the Arctic has warmed at roughly twice the rate of the global average. Summer sea ice extent has declined. Snow cover duration has shortened. Darker ocean and land surfaces absorb more solar radiation, further accelerating the warming. This is well documented and not seriously disputed in the scientific community. But the implications for jet stream behavior are where the controversy begins. If the Arctic is warming faster than the mid-latitudes, then the temperature gradient between the pole and the equator is weakening. A weaker temperature gradient should, in theory, produce a weaker and more meandering jet stream. A more meandering jet stream should exhibit larger amplitude waves, bringing Arctic air farther south and tropical air farther north. This could increase the frequency of extreme weather events, both cold snaps and heat waves, as the jet stream becomes more prone to forming persistent ridges and troughs. This hypothesis was first proposed in the early 2000s and has been refined and debated ever since. Proponents point to observed increases in high-amplitude jet stream patterns, particularly during certain seasons. They note that some of the most extreme weather events in recent years, including severe winter storms and prolonged droughts, have occurred during periods when the jet stream exhibited particularly exaggerated wave patterns. They argue that the statistical evidence, while noisy, suggests a trend toward increased jet stream waviness. Critics counter that natural variability in the climate system can easily produce multi-year or even multi-decade trends that have nothing to do with long-term climate change. The atmosphere is chaotic. It oscillates. El Niño and La Niña, events in the tropical Pacific, influence global weather patterns on timescales of years. The North Atlantic Oscillation and the Pacific Decadal Oscillation operate on timescales of decades. Teasing apart the influence of Arctic amplification from these natural modes of variability is extraordinarily difficult. It requires long datasets, sophisticated statistical techniques, and careful controls for confounding factors. And even then, the signal might be too small to detect definitively. There's also disagreement about which seasons matter most. Arctic amplification is strongest during fall and early winter, when sea ice loss is most pronounced. But the polar vortex and severe jet stream amplification tend to occur during mid to late winter and early spring. The timing doesn't perfectly align, which raises questions about whether Arctic amplification is directly influencing the polar vortex or whether other mechanisms are at play. But here's what we can say with reasonable confidence. The jet stream is variable. It always has been. But the amplitude of that variability, the extremes of the waves, may be increasing. Whether that increase is driven by Arctic amplification, by natural cycles, or by some combination of both, is still an open question. What's not an open question is the impact. When the jet stream amplifies, extreme weather follows. And if those amplification events are becoming more common, even slightly, then we're entering a climate regime characterized less by steady trends and more by variability extremes. Think about what that means for society. Infrastructure is designed based on historical climate data. We build flood defenses for the 100-year flood. We design power grids for the coldest expected temperatures. We engineer drainage systems for the heaviest expected rainfall. But if the extremes are shifting, If the jet stream is delivering weather that falls outside the historical envelope, then our infrastructure might be inadequate. The 100-year flood might become the 50-year flood. The coldest expected temperature might be surpassed multiple times per decade. The entire framework we use to assess risk and plan for the future might need recalibration. There's also the concept of hydroclimate whiplash, a term coined by researchers studying precipitation variability. The idea is that regions might experience rapid swings between extreme wetness and extreme dryness, driven by shifting jet stream patterns. One year, devastating floods. The next year, crippling drought. The average precipitation might not change much, but the distribution becomes more volatile. Farmers can't plan. Water managers struggle. Ecosystems are stressed beyond their adaptive capacity. It's variability, not steady change, that poses the greatest challenge. California is a textbook example. Over the past decade, the state has lurched from severe drought to catastrophic flooding and back again, sometimes within the span of months. The jet stream patterns responsible for this whiplash are exactly the kind of amplified, persistent configurations we've been discussing. A stubborn ridge parks over the west coast, blocking storms and triggering drought. Then the pattern flips. A persistent trough opens the floodgates, and atmospheric rivers dump months' worth of precipitation in days. Neither state is normal. Both are extremes, and the transitions between them are jarring. Now, zoom out even further. If jet stream instability is increasing, it's not just a regional problem, it's a hemispheric problem. The same mechanisms driving extreme weather in North America are also influencing Europe, Asia, and potentially even the Southern Hemisphere. We're all connected by the same atmospheric circulation patterns. A disruption in one region can propagate downstream, influencing weather thousands of miles away. The system is global, interconnected, and maddeningly complex. But complexity doesn't mean unpredictability. In fact, recent advances in technology are giving us tools to navigate this complexity in ways that would have seemed impossible just a decade ago. And those tools might fundamentally change how we forecast, prepare for, and respond to severe weather. Weather forecasting has always been a race against time. The atmosphere evolves rapidly, and the further into the future you try to predict, the less certain the forecast becomes. Traditional numerical weather prediction models solve complex equations that describe atmospheric motion, thermodynamics, and moisture transport. They divide the atmosphere into a three-dimensional grid and calculate how each grid cell evolves over time. It's computationally intensive, requiring some of the most powerful supercomputers on Earth. And it works. 7-day forecasts today are as accurate as 3-day forecasts were 30 years ago. The progress has been extraordinary, but there's a limit. No matter how powerful the computer, no matter how refined the equations, chaos theory imposes a fundamental barrier. Small errors in the initial conditions, tiny uncertainties in the current state of the atmosphere, amplify over time. Beyond about 10 days, deterministic forecasts become essentially meaningless. We can make probabilistic forecasts, ensemble forecasts that explore a range of possible futures. But we can't tell you with certainty what the weather will be 2 weeks from now. The atmosphere won't let us. This limitation isn't a failure of technology or intelligence. It's a fundamental property of chaotic systems. The mathematician Edward Lorenz discovered this in the 1960s while running weather simulations on an early computer. He found that rounding a number from 0.5, 06127, to 0.506 produced dramatically different forecasts after just a few simulated days. He called it sensitive dependence on initial conditions. The media called it the butterfly effect. The concept is simple, but profound. A butterfly flapping its wings in Brazil could theoretically set off a chain of events that leads to a tornado in Texas. Not because the butterfly caused the tornado, but because the atmosphere is so interconnected, so sensitive to tiny perturbations, that prediction beyond a certain horizon becomes impossible. So forecasters have focused on improving short-term predictions, particularly nowcasting, the art and science of predicting weather over the next few hours. Nowcasting is critical for severe weather. When a thunderstorm is forming, when a tornado is about to touch down, you don't have days to prepare. You have minutes. The faster you can identify the threat, the more lives you can save. And this is where artificial intelligence is beginning to revolutionize the field. Machine learning models, particularly deep learning neural networks, can ingest massive amounts of data and identify patterns that human forecasters or traditional models might miss. Satellite imagery, radar data, surface observations, atmospheric soundings, lightning detection networks, all of it can be fed into an AI model trained to recognize the early signatures of severe weather. The model learns from historical data, thousands of past storms, and develops an intuition for what a pre-tornadic environment looks like, what a developing squall line looks like, what distinguishes a garden variety thunderstorm from a supercell. The key advantage of AI in this context is pattern recognition at superhuman speed. A human forecaster, no matter how experienced, can only process so much information at once. They might be monitoring radar returns from 6 different thunderstorms, checking surface observations from dozens of stations, reviewing satellite loops, and answering phone calls from emergency managers all simultaneously. Cognitive overload is real. Details get missed, subtle signals get overlooked, but an AI model doesn't get tired. It doesn't get distracted. It can process data from thousands of sensors simultaneously, comparing the current atmospheric state to every similar situation in its training database, and flag potential threats in seconds. Some of the most promising research involves using AI to predict mesoscale convective systems, the organized clusters of thunderstorms that produce widespread damaging winds and tornadoes. Traditional models struggle with mesoscale prediction because the processes occur on spatial scales of tens to hundreds of kilometers, right at the edge of what global models can resolve. The equations governing thunderstorm development involve complex interactions between temperature, moisture, wind shear, and instability, all varying rapidly in three-dimensional space. Numerical models can capture the large-scale pattern, the overall setup, but they often miss the specific details that determine whether a particular storm will explode into a tornadic supercell or dissipate harmlessly. But AI models, trained on high-resolution radar data, can detect subtle organizational patterns minutes or even hours before a storm fully develops. They can recognize the early stages of rotation within a thunderstorm. They can identify the telltale signature of a rear flank downdraft beginning to wrap around a mesocyclone. They can spot the hook echo forming on radar that often precedes tornado formation. And because they're trained on thousands of historical cases, they can distinguish between storms that look threatening but remain benign and storms that are about to turn deadly. Imagine a scenario where, instead of waiting for a tornado, warning to be issued after a funnel cloud is spotted, an AI model predicts, with high confidence, that a specific thunderstorm cell will produce a tornado within the next 30 minutes. Emergency managers could activate sirens earlier. People could seek shelter sooner. The lead time, currently averaging around 13 minutes for tornado warnings, could potentially double or triple. In a tornado situation, those extra minutes are the difference between life and death. Consider what 13 minutes means in practical terms. You hear the siren. You grab your family. You move to the basement or an interior room. You huddle and wait. If you're at work or school, you move to designated shelter areas. 13 minutes is barely enough time to execute these actions, especially if you're caught off guard or if children or elderly people need assistance. Now imagine having 30 minutes, 45 minutes, an hour. People could leave work early. Schools could implement orderly evacuations. Emergency responders could pre-position resources. The entire calculus of risk changes when you have more time. But AI forecasting isn't without challenges. One of the biggest is trust. Forecasters have spent their entire careers developing expertise, learning to read radar signatures, to interpret atmospheric soundings, to recognize environmental setups. They've built mental models based on experience. Now, you're asking them to trust a black box, a neural network whose decision-making process isn't fully transparent. If an AI model predicts a tornado and none occurs, forecasters lose confidence. If an AI model misses a tornado, people die. The stakes are enormous, and the margin for error is slim. This trust issue isn't unique to weather forecasting. It's a challenge across every field where AI is being integrated into high-stakes decision-making. Medical diagnosis, autonomous vehicles, financial trading, criminal justice. In each domain, the question is the same. How much do we trust the machine? And when the machine makes a mistake, which it inevitably will, how do we respond? Do we abandon the technology? Do we refine it? Do we use it only as a supplementary tool, always requiring human confirmation before acting? There's also the question of responsibility. If an AI model issues a false alarm, who's accountable? The developers who built the model? The forecasters who chose to trust it? The agencies that deployed it? These aren't just technical questions. They're ethical and legal questions that society hasn't fully grappled with yet. And as AI becomes more integrated into operational forecasting, these questions will become more urgent. False alarms carry real costs. People evacuate unnecessarily. Businesses shut down. Emergency resources are mobilized. And perhaps most damaging, public trust erodes. If the AI model cries wolf too many times, people stop responding to warnings. They become desensitized. And when the real threat arrives, they don't take it seriously. This is already a problem with traditional tornado warnings, which have a false alarm rate of around 70%. That means 7 out of 10 times a tornado warning is issued, no tornado actually occurs at the warned location. Some of these are near misses, where a tornado forms but doesn't quite reach the warned area. Others are genuine false alarms, where the storm environment looked tornadic but never produced. Adding AI into the mix could improve accuracy, but it could also, if implemented poorly, make the false alarm problem worse. Despite the challenges, the trajectory is clear. AI is going to play an increasingly important role in weather prediction, particularly for short-term, high-impact events like severe thunderstorms and tornadoes. The models are improving rapidly. Some experimental systems have already demonstrated skill exceeding traditional approaches in specific situations. It's not a question of whether AI will transform forecasting, but when and how. One approach gaining traction is hybrid forecasting, where AI models work alongside traditional numerical models and human forecasters. The AI provides rapid pattern recognition and threat assessment. The numerical models provide the physical understanding and longer-range context. The human forecaster synthesizes everything, applies local knowledge and experience, and makes the final decision about whether to issue a warning. This collaborative approach leverages the strengths of each component while mitigating their individual weaknesses. The AI doesn't replace the forecaster. It augments them. And the timing couldn't be more critical. If the atmosphere is indeed entering a more volatile regime, if severe weather seasons are shifting, if jet stream instability is increasing, then we need every advantage we can get. Better forecasts, faster warnings, more accurate predictions. The tools we relied on in the past might not be sufficient for the future we're heading into. Think about the current outbreak racing across the Gulf Coast tonight. The pattern is complex, the timing is unusual, and the ingredients are aligning in ways that challenge our seasonal expectations. An AI model trained on decades of spring, severe weather data might struggle with a February outbreak that exhibits characteristics more typical of April. The model's training data might not include enough similar cases. This is called distribution shift in machine learning, where the real-world conditions deviate from the training data. It's a fundamental limitation that researchers are actively working to overcome, but it highlights the need for continued human oversight and adaptive learning systems that can update themselves as the climate evolves. So here we are, in mid-February 2025, watching multiple severe storms race toward the Gulf Coast, watching Arctic air plunge into the east, watching the atmosphere fire on every cylinder simultaneously. We're witnessing a complex, interconnected weather pattern driven by polar vortex dynamics, amplified jet stream waves, and persistent temperature contrasts. We're debating whether tornado season is shifting, whether the sun plays any role, whether climate change is making these events more common. We're developing new AI tools to predict the unpredictable, and through it all, the fundamental truth remains unchanged. The atmosphere is a chaotic system, capable of extraordinary violence and beauty. Governed by physics, we understand but can't perfectly predict. We live at the bottom of an ocean of air, subject to its whims, vulnerable to its extremes. But we're not helpless. We observe, we model, we forecast, we adapt, and with each storm, each outbreak, each surprise, we learn a little more about the planet we call home and the forces that shape its weather. The worst might still be coming. Not just tonight's storms, but the cumulative challenge of navigating an atmosphere that refuses to sit still, a climate system in flux, and a future where the old rules no longer apply with the certainty they once did. But we face it with better tools, deeper knowledge, and a growing understanding that the weather, for all its chaos, follows patterns we're just beginning to decode. And maybe, just maybe, that's enough. Subscribe to follow this story to its conclusion, because what happens tonight across the Gulf Coast is only one chapter. The jet stream remains amplified, the pattern still locked in place, and the conveyor belt of instability continues running toward an endpoint we can't yet predict. Communities brace, forecasters recalculate, and somewhere over the warm Gulf waters, the next round of storms is already organizing. You'll want to know when it finally breaks.